Fine. Well, many of you asked about references, and as a first input, I wrote there on the table some basic references to what I've said. Essentially, I mentioned two books. One is the book by Breuer and Petruccione, whose first edition goes back to 2002. This actually is not simply a book on open quantum system. I would say it is the book on open quantum system, so a very valuable publication. There is also a more recent contribution, smaller in amount, but pointing to some more recent result if you want. It's a booklet published by Springer, by Rivas and Huelga. And of course, I've been biased a bit by the lecture notes I prepared for my students in Milan. So some part of the stuff and some other references you can find there for free. And maybe this doesn't cover exactly everything which I've prepared out, but maybe for the end I will give you a printout of a more detailed reference. These are the basic ones, so they're more enjoyable and more wide in scope. So we were dwelling with our projection operator technique, which I introduced essentially to say, okay, so it is in principle possible, given a microscopic dynamics, to write down at least formally the exact evolution equations. In particular, I pointed to the fact that if one introduces a projection operator, which is useful to the extent to reduce the amount of degrees of freedom you are taking care of, but still enough to give you the dynamics of the reduced system, then you can come, even though I didn't go through the details, but you can believe me that you come to a closed evolution equation for the so-called relevant part of the statistical operator. Rho of t is now an operator referring to both system and environmental degrees of freedom. Following the procedure I mentioned before, I came to one kind of evolution equation, which was of integral form. So it was the integral between 0 and t, the variable the tau, of a certain kernel depending on t and the variable tau, acting on p applied to rho of tau. So this is a proper integral equation with an integral kernel, in principle very difficult to solve. You can go through a similar path, so always use this idea of projecting the equation of motions on the relevant part, which you call P of rho, and the other contribution, which altogether make up the whole statistical operator. This is sometimes called irrelevant part. Relevant or irrelevant is simply reflecting our viewpoint. This is what we are looking for in order to recover the system state. This is what we are not interested in. Now, you can go through a similar path and end up with an equation which is local in time. So you come to an operator, let me call still k, since it depends on only one time, so there is no confusion here, which acts on p rho of t. So this is an equation local in time. So there are two analog perturbative techniques which leads to formal exact equations, the one in integral form, so-called the Nakashima-Zwanzig, and the other in a time local form. This is called the time convolutionless approach. Now, what do they have in common? They have in common the fact that for both of them, by taking the partial trace with respect to the environmental degrees of freedom, we end up with an equation which gives us exactly the evolution in time of the object we are interested in, which is the reduced statistical operator of our system. In the one case, this will be written as a kernel, which is not exactly this one. Now we are taking the partial trace, so it's a transformation of this object. So I'll use a different name. So an integral of tau, properly called the Nakashima-Zwanzig kernel. This is an operator at the level of the system only, still depending on two times, acting on the statistical operator of the system, which depends on the elapsing time. So in principle, to solve the equations, you need to know the state of the environment through time. So this is typically associated to a notion of memory, and we will try to see that this might be the case, but it's not necessarily the case. On the other side, we end up with a another contribution, which I write with a FedEx TCL, to mean that this is actually an operator at the level of the system only, which provides you local in time evolution equation for your statistical operator. Of course, there are a lot of details in between, but what I wanted to point out that there are essentially two classes of evolution equations, which you can find out, the one in integral form, the other in time local form. If you retain all perturbation orders, these are exact equations. So in particular, they preserve not only trace, but also positivity, and they are completely positive maps. The problem or the difficulties arises when you start doing a perturbation expansion, and typically what is done is to restrict to a second order perturbation, which for the Nakajima-Zwanzig kernel leads to an equation of this form, which you might have encountered before. So you retain an integral over time, and what you have here, second order means that the operator L of t, the Liouvillean I introduced before, which was given by the commutator with the interaction term in interaction picture, appears twice, essentially. So the structure of this equation is as follows: the trace over E of the commutator of the interaction Hamiltonian time t, commutator with the interaction Hamiltonian interaction picture time tau, with rho s of tau tensor rho a. And this comes about because we have applied once projection operator, which in standard form means take the partial trace, obtain the reduced state, and make it tensor product with a fixed state on the side of the line. So these are double commutators, and I end up with them. So you see this is a typical structure, but this structure doesn't warrant complete positivity. So one can indeed see that if you end up at this perturbation level, which is in second order in the coupling, this is a first approximation which doesn't necessarily guarantee that your time evolution is well behaved. A similar result can be obtained for TCL. If you go to TCL up to the second order, you obtain the very same expression where here you recover your statistical operator at the given time. This corresponds to the fact that indeed this has to be a local in time evolution equation. So also from the simple fact that at the second order you obtain different equations, you realize that they are in general not exact. So they don't give you the exact time evolution. It's a matter of conveniency which one you're going to consider. Of course, the one local in time is easier to be evaluated. This integral equation generally has better properties as far as convergence is concerned. Please. Perturbation expansion is, suppose you put in front of your interaction term a coupling term lambda, a dimensional, which you later put equal to 1. This is the order of the perturbation. Now, this said, I go for the first example, which is meant as part of a tutorial, so I try to introduce them stepwise along the lectures. An example, which I will present sketchily, but where you first see the appearance of these concepts I introduced before. So, what do I take as example? Suppose you have a two-level system. So we have a two-level system, and the separation among levels is fixed by an energy scale, say, omega 0, take h bar equal to 1. This system is then, so this is our system in our picture, and this system is coupled to a collection of bosonic modes characterized by certain frequency, omega k, and there is a certain coupling whose strength is given by certain constants g sub k. In principle, you consider many of these modes, possibly the numerable set, which is a possible model to mimic the action of a proper bosonic field. So, in the essence, we have a two-level system coupled to bosonic reservoir. The Hamiltonian of the system, in this case, can be taken of the following form. So this is sigma z, standard Pauli operator. This is the difference among levels. for the environment, I consider a set of harmonic oscillators with frequency omega k, and I introduce the annihilation and creation operators such that the commutation relations indeed corresponds to bosonic modes. And now the point is how to characterize the coupling. We characterize the coupling as follows. We take a coupling which commutes with the system Hamiltonian, which will mean that this interaction will only affect the coherences but not the populations of our system. And the interaction can be written as sigma z times, in the sense of tensor product, we are the operator part of the side of the environment. We take a sum over k of gk dk dagger plus gk complex conjugate dk. So it is a linear combination, and B and B dagger essentially kind of position coupling. This is the choice of this coupling is due to the fact that this leads to a typical dephasing effect, so affecting the coherences of our quantum system. It is a quite widespread situation in the, if you consider a system which might be an atom or whatever, coupled to a complex environment which only affects the coherence. They don't drive excitations, they don't exchange direct excitation with the buff, but the dynamics is affected through the coherence. Now, the point is that this simple situation can be exactly solved and still be of interest in many situations. Also in quantum biology, is typically taken as a relevant coupling when you want to describe the coupling between your system and the environment. The fact that HS commute with interaction allows you to exactly solve the dynamical equations, which means that in this case, we can exactly write down the map and check all the properties we introduced before. So let me start on this side of the blackboard. In principle, what we have to do, if you are able to, is to obtain rho s at time t as a partial trace over the environmental degrees of freedom, which means over the bosonic modes in this case, given the overall interaction Hamiltonian, which is now known since we fixed all elements. Take an arbitrary initial state for our two-level system. Tensor product the state, which is assumed to describe the bosonic modes, which we take generally to be of thermal state. So E to the minus beta HE, beta is the inverse temperature over a contribution which fixes the trace, US E T dagger. Now, the point is that this can be exactly evaluated because this object is essentially known. The idea behind this is that given the value of sigma z, you have a certain action, a displacement actually on the state of the environment. So if you accept this, you easily find out that a matrix representation of the state in evolved time is such that the diagonal matrix elements, which represents population, so in a sense the classical degrees of freedom, if you want, stay unchanged, while the off-diagonal ones are modified by multiplication to by a certain function, which is now convenient to write in this form, e to the minus gamma of t. Yes? Please. Okay, I slow down. So maybe I will put less content, but okay. No, it's fine. I mean, it's more important to convey something than to come to a certain goal. So I hope up to now everything is clear. Of course, there is, there are in between a lot of calculations, no? But this you can take for granted if you want, or find, for example, in textbooks. Now the idea is to concentrate on the main points. So I give you the idea why this can be evaluated, essentially because the Hamiltonian of the system commutes with the interaction Hamiltonian. So in a sense, this is a simple situation. So given that this can be calculated, you indeed obtain this, this operator and evaluate the partial trace, coming to the following result. The idea is that indeed this is a two-dimensional system, which means that all that you have to check in the essence is how this matrix element behaves in time, because they are on the diagonal fixed by trace preservation, and how these elements behave in time, because they are fixed by taking the complex conjugate. So essentially, you have to take care of the two elements. This is fixed because sigma z commutes with interaction Hamiltonian, so it does not evolve in time. So in the very end, you have to evaluate these matrix elements. So everything boils down to put here this element, which would be the off-diagonal element, and see how it evolves. Okay, so this is something that you can trace back. If you do this, you end up with an effect which is simply multiplying the initial value times this function. How does this function looks like? So this function gamma of t can be written as follows. It is given by an integral over frequency of a certain function, which I will now explain more in detail, j of omega, which is called spectral density. And this contains the information about the modes of the system, the coupling to the environment. We'll come to this in a minute. I prepare now to finish this expression. A contribution which actually takes into account the fact that your environmental system has in principle a finite temperature. This can vary from 0 to plus infinity in principle. And this is given if you work out the calculation by hyperbolic cotangent with argument beta omega over 2. And another factor, which is 1 cosinus omega t divided by omega squared. Now, of course, this comes out of the calculation. The important fact is this takes into account the properties of the environmental state. It's a thermal state, and dependence of temperature appears here. And this quantity, this so-called spectral density, can be written formally in this way. So what you end up with is a calculation in which if you replace j of omega by a sum over k label the modes of the environment, and you take the coupling constant squared, so g sub k whole square, times a Dirac delta omega minus omega k. So you would, if you insert this expression here, you will end up with a sum over k of modulo square of gk and this different function evaluated omega k. This is what exactly comes out of the calculation, because as said, in principle, our expression for the environment is not over a continuum of modes, but over a denumerable set. Then it's kind of a way to take the, if you want the limit of infinite modes, you take this whole this expression as a whole. It contains information both on the frequencies on the side of the environment and on how strongly each frequency is coupled to the environment. So it contains information both on the environment and on the coupling. So it characterizes not only the environment, but also the dynamics overall. So this is the object which is usually modeled, since in order to know it in detail, you should really assume that you have a finite or denumerable set of modes. For each of one, you are able to measure the coupling strength, which is really, in general, not feasible. But it is can be taken as a general mode in which you have a lot of bosonic modes coupling with your system, so many that you only give an overall effective description, and characterizing the properties of this function gives you information about this coupling. Typically, what you would have is the fact that if omega is very large, this function has to go to 0, meaning that your system is coupled to the environment only up to a certain frequency. So it responds, it is affected only by frequencies up to a certain finite value, okay? Which is a kind of realistic situation. So it's not, there is not coupling at any arbitrary energy, only to a certain value. And the coupling gets down if energy goes up. The further information that you get is, given a certain frequency, how strong is the coupling? And this is reflected in the amplitude of this function at the given frequency. So it's a way to effectively convey information about the system and the environment when they're coupled together. So it's an effective way. And the name spectral density comes from the literature. It's not related actually to a proper mathematical concept. Now, we have the map. In principle, we already know that this is a completely positive map, because if you believe that this was the exact calculation, this is so. But maybe it's in this case, it is convenient to also have a look at the Choi matrix. So let me see it in a specific example. So if we now evaluate the Choi matrix, what we have to do? As I said, it was a n square times n square matrix. So this time is a 4 by 4 matrix. Yes, please. Typically, the behavior of low frequencies is very relevant, and there are classes of spectral density which are actually characterized essentially by a choice of cutoff, which is usually not so important. I mean, whether the cutoff is exponential or as a power law doesn't make a big difference. But the behavior at low frequency, which is typically taken to be a power law, it's quite important. And depending on this behavior, so the behavior of spectrum is low frequency, you have different behavior for your system. Yes. Yes, in order to have convergence of this integral for sure. Yes. So this is somehow, these are, if you want, constraints that you put on the reliable J of omega that you consider. So integrating up to infinity is usually solved by taking a suitable cutoff in this function. And the behavior for small omega is checked also depending on the temperature bands. Yes. This is a phenomenological modeling, essentially. So what we obtain from the exact representation is that if we put all information in this expression, this is where somehow we have the freedom to play in order to describe different environments, which all share the fact that they do affect our system simply by a modification of the coherences. Okay, so in a sense, it's a specific model which allows to consider a phenomenological approach. Okay. Now, as I said, the Choi matrix is in this case 4 by 4. The first block would be our map phi applied to the element 1, 1. So it says how a state which is characterized by value 1 in the upper state and 0 everywhere else is transformed. This is the first block. Then you would have another block when you apply phi to 1, 0. And the same for the other two. Now, if you apply it to 1, 1, what happens? It remains as it is. So it's just 1, 0, 0, 1. It is not transformed. The same goes for the other block here. If you apply it to the metric which has only 1 at the bottom right corner, it remains equal to itself. The only effect is in the coherences. So in this off-diagonal, you have the transformation of the off-diagonal term, which is multiplied by itself by this factor e to the minus gamma. So you would end with 0, 0, e to the minus gamma t. So, and of course, it is then symmetric in this case. So this is an explicit representation of a Choi matrix, and if you counter-diagonalize it, you obtain the eigenvalues, and you can end up write down your transformation in Krauss form. In the following setting, this Krauss form is quite simple. You essentially have two Krauss operators, sigma z and the identity. So you have a first contribution with the Krauss operator, which is sigma z, where the time dependence is only in this three-factor, which are essentially the eigenvalues. This is always a sorry. Okay. This is a quantity which is always positive, because this quantity is less than 1. The other contribution has a prefactor which is 1 plus the exponential of this function times the Krauss operator, which is the identity. If you have a look, what you realize is that the diagonal matrix elements are not affected, by the others are exactly multiplied by this exponential. So, as a result, what you see is that in this simple case, you end up with 2 Krauss operators, which essentially describe the phasing. They are obtained by diagonalizing this object. And these 2 coefficients can be, if you want, can be reabsorbed in the Krauss operators. The point is that they are positive. So you could take square root here and square root here and the same. So the example is very simple, but is instructive, because everything is under control. More than this, given the exact evolution mapping, where you check complete positivity and Krauss representation, you can also look for the time derivative of this object and see whether you can find out the expression of the evolution equations. Up to now, we have only performed an exact evaluation of the operator at time t. Let's look at the evolution equation. Because in the general case, you will not be given the exact mapping, but maybe you can have or look at the evolution equation. Now, if you do that, this time by simple calculation, but still by calculations, we'll find out that the time evolution of your system operator looks like this. We know that this can be either in the integral kernel form or time local form. For this model, it turns out that this can be written in time local form. Here you have a contribution which is simply the free Hamiltonian. And the other contribution depends on this function gamma of t, which is determined, this dot means the derivative with respect to time, which is determined at the spectral density, which contains the information about the environment, both its temperature, the available frequencies, the coupling to the system. And as the spatial form, you have this operator sigma z, rho s sigma z. Let me put an adjoint, even if it is meaningless, but just to point out the structure. Of course, this sigma z is self-adjoint, but this points to a more general structure. Minus 1/2. I write another nonsense, but simply to put into evidence a structure. This parenthesis means the anticommutator, so it's operator times rho s plus rho s times operator. And this is, in this case, simply the identity. But what I wanted to put into evidence, you have an operator, the adjoint to the right, and this structure. Okay. And this comes out exactly. Now, I've not said that these quantities are necessarily positive. This is maybe not necessarily the case. I just put it into evidence. However, we know that whatever the expression of these quantities, provided they are evaluated as such, the solutions of this equation for any arbitrary initial state are well-defined transformation, so sending positive operators, preserving trace, and moreover, a collection of completely positive transformations. Now, this, in a sense, is maybe enough to point to a simple example which you can work out by yourself, in which you have all the ingredients, the structure of the mapping, the associated matrix, the related Krauss representation, and you can also find out the evolution equation, and this special operator expression appears. Now, as a second part in this introduction to open quantum system, I would like to focus on possible sensible evolution equations, because in general you will not be able to perform an exact calculation as performed here. Now, this is the exception rather than the rule, of course, even though it can be instructive. Yes, please. Sigma z, yes, thank you. Yes, for sure. So this is the free contribution. Yes, thank you. Okay, So now I move to a general possible treatment of evolution equations. So this part I will call the Lindblad theory. And yes? What do you mean? Well, for any strength? So the constraint is only that the integral of the spectral density is convergent, so it makes sense. No, this is not correct. So what I've said is that I take an initial state which is of factorized form, or S times 0, times the state which is of a thermal state. So I've used a specific class of states. I'm not saying that for an arbitrary form of the environmental state I'm able to do the calculation. But given that, if you were able to give the expression, in this case you formally are, to give the expression of the state of the environment with elapsing time, this in general will evolve itself. Okay. So as a matter of fact, the state at initial time is factorized, but with the elapsing time, the state gets correlated. Then, of course, there are cases in which the state of the environment is really does not change in time, but that's another point. So they get generally correlated. This is in the first instance. And in the second instance, even if you trace out over the system degrees of freedom, so suppose you can do that, you have a state of the environment which changes itself. In a sense, the situation is in principle such that you can exchange system and environment. It's label that we give to the system. The point is the labels are motivated because we have a two level against a whole set of bosonic modes. But depending on what you're interested in, I will, if I may, because it looks like I'm not going so far, but if I may, I will come to a situation in which you are interested in the dynamics of the field, which is an infinite dimensional interface, and you affect it by letting this mode of the electromagnetic field interact with atoms going through a cavity in which the field is stored. So really, system is the degrees of freedom you are considering and interested in. So, typically, the idea is that system is simple and the environment is complicated, but it's up to you in a sense. So, Lindblad theory and generalized master equation. The idea that Lindblad theory is most textbook and generalized is a bit more not up to date, but it's more recent developments, if I may. So we said if the initial state is factorized, we do have the quantum dynamical map. It exists, but how does it look like? Apart from very special cases, you don't know what the structure is. But you may look for results which give a characterization of classes of this. In particular, consider a situation in which you take your initial state, you go to a state at a later time, S, by applying your map, phi of S, and then you go still forward in time for another time, let's call it t, and you end up with rho s at time s plus t, because overall your path was s plus t. And suppose that this is the same as making it in one shot, so applying the map phi t plus s. What you're saying in a sense that in order to proceed onwards in time, you only need to know the state at the given time. Now, this picture corresponds to a so-called semi-group composition law. is the time evolution up to time t plus s can be equally well obtained by splitting the evolution in two, and if you can split it in two, you can split it in even more pieces, obviously, over times t and s, with the only constraint that t and s have to be positive, so onwards in time. Here we are introducing irreversibility. So for this class of objects, which is not a generic class now because we have this spatial composition law, there is a general mathematical results which tells you that they can be written as the exponential of t times a certain operator, which I call L, it's often called Liouvillean. If you want, this is a super operator. Usually instead of the word super operator, I have used the word map. Map sends operators to operators. These objects are often called super operators. Operators send vectors in the space to vectors. Super operators send operators to operators. I usually use the word map, but another equivalent terminology is super operator. So this is a general result, but the point is, do we know how L looks like? Otherwise, it's kind of a rewriting in our view. Now, for a physicist, you really want to have a look at this object, whether you can combine this object with some physical intuition. Now, on top of this, so on top of the semi-group composition law, you further ask that each of these map is CPT. It is to say, completely positive and trace preserving. And this is not a difficult part, but it's still relevant. The idea is that it's written in this expression. For t equals 0, you recover the idea. So t equals 0, you are not changing the state, and you proceed forward in time. Now, in this setting, you have a beautiful and well-known result, which is also a theorem and becomes a theorem when you introduce suitable hypotheses. I will be more sloppy, of course, but the basics are there. So, yes? Yes? How it appears? You mean how to go from this line to this line? Okay. On the one hand, it's a theorem. On the other hand, think about numbers. Functions which combine in this way are given by exponentials. So this, in a sense, is enough to get the idea. This is the function. I'm not imposing the semi-group condition, actually, but this is a nice point. I say, if I have a semi-group composition, then I will go on. Of course, one might ask the question, when do I have a semi-group composition law? This is a feasible question. And sorry? Yes, for sure. And this is the motivation for my lectures, essentially. So coming to a non-Markovian situation. But nevertheless, this is a very interesting situation because we can characterize it. And moreover, when does it apply? A typical situation in which it applies is the situation in which there is a clear separation of time scales between system and environment, which means that in some sense the environment relaxes very quickly with respect to the typical time scale of the system, so that in a sense the system is always interacting with a new environment, if you want, or environment which is in this state which has remained fixed. So typically in this situation, such an approximation holds. Of course, to hold it exactly, one should check it in principle, no? Which is a very difficult point. But it looks like in many relevant situations, this is a sensible approach, and this can be seen by the fact that we will come now to a characterization of these operators in this setting, and they describe fields quite well. But of course, this is not the most general situation, and when I will come, if I ever come, to characterize the different quantum processes, as I said in the morning, the idea is given a quantum process, see how it might look like, see what are the related evolution equations, distinguish among processes which have or do not have or imply memory effects. And these memory effects are for sure related to this property. In fact, what I said here, I said, in order to go onwards in time, you only need to know the state at a given time. This was preparing the ground for a violation of this condition, for preparing the ground for an idea of memory. But first I have to introduce the memoryless case. So there is in this connection, there is a beautiful result, which is a theorem which was obtained in 1976. So it's by now exactly 40 years old. Indeed, this year there was a conference celebrating this 40th birthday of this theorem, which is known also called as GKSL theorem. Stands for Gorini, Kosakorsky, and Sudarshan, which in a paper which appeared in the same year as a paper by Lindblad, essentially characterized this generator under different mathematical hypotheses. This is a most well-known result, but it essentially says that this, yes? Sorry? These objects are called quantum dynamical semigroup, and the theorem will characterize this L. No, it's not reversible. Oh, wait a second. You think you put a minus here, but if you put a minus there, in general, you will not have a transformation which is completely positive to 7. So this only happens if you have a unit evolution. So it's not reversible. If it's unit, it's reversible. So when you speak about an inverse, if you want to speak about an inverse in this setting, you mean not only a linear transformation, but a linear transformation which sends states to states. And in this sense, it is not reversible. This is the same argument holds in the classical setting. So you can speak about semigroups in the classical setting. And indeed, this theorem is a kind of quantum counterpart of a characterization that you have in the classical setting. So let me state, let's say that the collection of mapping phi of t, or positive t, is a quantum dynamical semigroup that is to say, it's characterized by this collection of statements. So composition as a semigroup, CPT at each time, at time t equals 0 is the identity. If and all if this operator L, which is typically called generator, can be written in this form. L applied to rho is equal to the commutator with an operator which is self-adjoint, plus a contribution, which is the following form, is the sum of a finite ordered enumerable, depending on the dimension of the space of the system, set of operators with certain numbers, which can be interpreted as rates because they are positive, and certain operators, let me call them L sub k, rho L sub k dagger, minus 1/2 L sub k dagger, L sub k, anticommutator with rho. As you see, this is exactly of the form that I obtained before, apart from the fact that here we are in particular saying that these coefficients have to be positive. These operators are often called Lindblad operators, but of course this is a matter of taste. And they are the natural point in which you insert some idea of what the interaction between system and environment looks like. They can typically be, I don't know, raising or lowering operator with respect to the ground or excited state of your atom, if you're describing as system and atom, or that it can describe collisions if the dynamic is driven by collisions. And this rate can be exactly the rate with which photons are emitted or absorbed, or collisions to take place, or a certain kind of collision to take place. So this is not only a mathematical result, if you want, it is, but it's also the place where you can put in a lot of physical intuition. This is perhaps the fact which has made these results so important. And it allows to describe a huge amount of interesting dynamics. The statement is that the solution of a equation of this kind is a semigroup of completely positive trace processing maps, and if you have a semigroup of completely trace processing maps, then the generator has this form. The generator L of rho is actually what we usually introduce to write down a so-called master equation. So what happens is that the derivative of the state at time t is equal to L applied to the state at time t. More standard terms, the derivative of rho s of t is equal to L applied to rho s of t. And this is what we call, typically call a master equation, and the name comes from the classical setting. So the equation in which you find the balance between the contribution of different terms. It can be seen as a gain term, and this is a loss term. Please notice, and I come back to the question by Professor Singh in the morning, even if rho is pure, this state is typically mixed. So this contribution leads you, it's a typically incoherent contribution which drives pure states to mixtures. So in this sense, even if you take as a particular situation the initial state which is pure, you are led to introduce statistical operators. And more, yes, please. I wouldn't say so, but on the other hand, first of all, we still have to define memory because it's a difficult topic. And also, I'm not aware of general characterization of nonlinear evolution equation, which still leads to well-defined. It's difficult to answer. There is little work on the subjects. On the one hand, of course, linearity of quantum mechanics plays an important role. And if you start in this setting, the evolution equations are naturally linear. So there is no restriction in this aspect. Yes. Yes. Because we are in the same, so the same kind of motivation applies. So the linearity of the equations follow from the fact that I start from a microscopic dynamics on a little space. There you have linearity, and this linearity goes on. Of course, you might have no linearity if you have a complex system and you have introduced some, I don't know, kind of mean field description, which also depends on the state. But then that is kind of a, I mean, an approximate description which does not come from an exact microscopic approach. So in this respect, linearity has to be retained. But it's a huge difficult subject. So we have introduced this basic result, and now what I would like to show is that, okay, this is a theory, it's an only. I will say something in the one direction in order to point to a generalization of the result. Okay, so something in the one direction means, suppose we have the solution of an equation of this form, let us show that it is a completely positive time evolution, and use this as a starting point to obtain generalized master equation or generalized evolution equations. So, The idea goes as follows. We write this generator as a sum of two contributions. One which we call relaxing and the other that we call jump. What we take as a relaxing contribution, the idea is that the relaxing part applied to rho is the combination of the unitary term, if you want unitary in the sense that if you only had this contribution, you would end up with a unitary term evolution. And the other term, which is the anticommutator. So the anticommutator of sum over k, lk dagger, ak anticommutator with rho. This expression can also be written as minus I, an effective Hamiltonian applied to rho, minus rho times the adjoint of this effective Hamiltonian. It is to say the loss term does not disturb the purity. It decreases the trace in general, but does not disturb purity. It is the same effect that you would have if you should introduce a so-called optical potential, so a kind of a non-self-adjoint Hamiltonian, which is an effective way, for example, to describe the absorption of the system. So this is what I call the relaxing part, and the idea is that the evolution due to this contribution, so the evolution over a finite time, this is the differential equation, is E times T L relaxing applied to rho. So this would be a semi-group of contractions. It doesn't destroy purity, but it decreases the norm in general. The other contribution, this Lj, is a jump contribution. This is the incoherent part. The term which I've written as Lj applied to rho is equal sum over k, Lk, rho, Lk dagger. Please notice that actually this object determines the whole Lindblad structure, because this term can be related to this other one as the adjoint action of the observables. This I give also as a, I'm not going into this detail, but just to those who are perhaps already aware of the Lindblad structure, I'll just point to the fact that in the essence, this map, which is by construction CP, as you can see immediately, but is generally not trace preserving, so it's simply CP. This is essentially the earth of all the expressions. So we have these two parts, the contraction term and the jump part. Now, the statement is that one can check that the time evolution map can be written as follows. As a sum of contributions in which you have first only a relaxing part, then the convolution between relaxing part and jump part. Now I write it in more detail. So you take the convolution of these two objects. I'm going to write it in more detail, but let me write it compactly right now. And you go on inserting each time another convolution. So this is formally an exactolution, and you can check it by derivation, which is it's also in a, if you want, in a perturbation expansion. And let me write it more explicitly here. So the state at time t can be written as follows. You take the map applied to the state at initial time, which means the first contribution is E the term times T LR applied to the initial state, so this contraction, plus this infinite amount of contributions, which are distinguished by the number of insertion of this map Lj, this jump part. So it's a sum from 1 to infinity, the integral between 0 to t in dtn, the integral in dt1 between 0 and time t2 of what happens. So I'm essentially this integral translate this convolution. No? The integral, I'm convoluting these objects. So you have R at time t minus tn, then I have the action of Lj, R times tn minus 1, and so on and so forth. Lj, R t1 applied to OS 0. So what I have done is writing down the formal exact solution of the master equation. So given that the master equation is in Lindblad form, so that I can split it into these two pieces. R of t is the solution for the one piece only. And the exact solution is obtained by inserting at intermediate times this, which I call jump operators, in that this Lj takes into account the action of these Lindblad operators, which are meant to describe the microscopic interaction events which drive the dynamics. So, I don't know, exchange of a photon or collision or whatever. This expression is indeed a solution of the master equation. If you take the time derivative and you have enough patience, you find that this time derivative is just L applied to rho at time t. And it provides you also in principle with a kind of interpretation if you want. So the dynamics is a sum of contributions described by the fact that you have first a relaxing evolution, then a jump, relaxing evolution, and a jump. And the overall dynamics is the sum of these evolutions, which would be known if you could say, okay, at time t1 I had the first jump, at time t2 I had the second jump, and so on and so forth, and sum overall possible number of jumps from 1 to infinity, and overall possible intermediate times. So integrate in this case because of time. Now, the idea is that given this expression of the solution, it's easy to generalize the Lindblad result to the so-called time-dependent case. So up to now, we had a proper composition law of a semigroup. All that mattered was the elapsed time. So the map actually did depend on a single time. Now, suppose to relax a bit the condition we had in the theorem, and we send our Lindblad operators to a possibly collection of time-dependent operators. So Lk becomes t-dependent. Gamma k also are allowed to become time-dependent, and it is not so strange. We have already seen in the example we have considered in the pure phasing model that indeed these coefficients appearing in the structure of the equation was the exact one. It was exactly in the Lindblad form. However, it allowed for time-dependent coefficients. So it's in a sense natural to allow for this generalization, but still keep them to be at any time possible. Now, if you do this, you have also to modify your R of t, which now goes over to an object which depends to an initial and a finite time. The point is that, in a sense, you're introducing time-dependent rates. So instead of a situation which is homogeneous in time, it's a situation which is no more homogeneous in time. So at what time you are considering a quantity, it does matter. So this object is replaced by a two-time object, and instead of simply the exponential of our L of R, we have the time-ordered exponential between 0 and t in the tau of L of tau, L sub R of tau, because now our Lindblad operators generally depend on time, and the same goes for the rates, so we have to do that. I notice now that, please forgive me, but I somehow introduced the rates in the definition of the operators along the way. Okay. It's not an important point, but just to be precise. Okay, so with this replacement, we end up with a map which is still of exponential form, and it can be formally written as the integral between 0 and t of the tau, our time-dependent Lindblad structure. So this is everything as before, only L depends on time. So instead of multiplying but the elapsed time, I integrate it over time. And since they are operators, I also have to take care of ordering in time. Now, how does this object look like? Now, the statement is that this object allows for the very same expansion if you want. And here what I do is simply replace the object depending on 1 time by the object depending on 2 times. So this relaxing part does not only depend on the elapsed time between t sub n and t, but on the initial and the final time, and in between the decaying rates, for example, do change. On the same footing, this Lj will now generally become time-dependent operators because they keep the same definition, but here we insert time dependence. So, as you see, in such a way, you can almost with the same effort, apart from operator ordering, introduce a structure of generator which leads to a time evolution. But is it still completely positive? Yes. Why? Well, simply for the fact that where do we read complete positivity here from the solution? So I said this is the solution of the equation, but one should have already asked, but yes, but is it CP? Yes, it is completely positive. Why? Because it is sum or composition of completely positive maps. So from the structure of the solution, we immediately see that it is completely positive. But this remains true if we replace this object with time-dependent objects. So by the very form of the solution, we can conclude that indeed this is a well-defined time evolution which is complete positivity. So seen in these ways, it's a kind of a simple generalization. What do these two approaches have in common? A feature that I would like to stress. Yes, please. The commutator vanishes, this contribution. No, because you need both terms. For trace preservation, you need gain and loss. So what can happen is that this contribution can be the identity. And then the anticommutator boils down to minus rho. This is a situation in which, for example, when the in-blood operators are unitary. But otherwise, if one is 0, the other has to be 0 for trace preservation. So they come together. Yes? One could make this statement in a sense. Yes. If you want, you would call this a dissipative term and this the noise term. In a sense, the whole Lindblad theory, open quantum system theory, came about because of looking of sensible description at the quantum level of dissipative effects. Because one had problem with preserving Heisenberg uncertainty relation, if you want straightforwardly use a classical approach, so one should be more careful and go through a more tactical. And the origin of all this, in a sense, is in that. If you have a quantum system, introducing dissipation is not so obvious because there are constraints on the noise in order to essentially preserve the Heisenberg uncertainty. So this comes about from a proper quantum treatment. Bring this with itself. But if you go phenomenologically, then it can be dangerous. And in a sense, these are results. There are, of course, many others, which tells you, okay, which are the sensible paths, even if you go for a phenomenological approach, but still these have all relevant quantum features. I don't know whether this answer. Gamma k is positive. Here, because when I want to say that Lj of t is still a CP map, as I stressed, this is the key point. And if I want Lj of t to be again CP, you might say, okay, the fact that L of L sub k is time dependent is not so important because I have the adjoint here. And this I can agree. But if these coefficients are not positive, this is not the CP map. Because we learned from the Krauss theorem that the map is CP if and only if it can be written in Krauss form, which means that these objects have to be positive. And then you can forget about them in a sense, putting them into the square root of this object is partly here and partly there. So that's what I use it. And they have all to be positive. You are asking now whether they were always positive in that example? No, they were not. As I said, depending on the spectral density, they are or they are not. Which, keep this in mind, conclusions will follow. Okay? Now, the point which is related actually to this question, as I said before, semi-group means I go from time 0 to s, applying the map once, and then I start from here. I don't need any other information. I come to the state at the final time, so to say. Or I do it in one shot and nothing changes. This is the semi-group composition law. Now, what I'm saying with this enlargement is that if I go from here to here, I hope you can see, I introduce a map phi from time 0 to time s. And in order to proceed onwards, I need a map which starts from s and goes to time t. Or, equally well, I can start from time 0 and consider the map going from 0 to time s plus t. So what do they have in common? Essentially, they have in common this fact that, let me consider s and t as the initial and ending time. I can split this evolution in two pieces, and if two, of course, many others. On the same footing, I can split the semi-group evolution into pieces. Here I have the constraint that tau is in between s and t, and here I have the constraint simply that the times are positive. Sorry. And what do they have in common? They have in common a property of divisibility. So I can always split the time evolution into pieces, as many pieces as I want. And each piece, so each of these operators is CP, and particularly trace preserving, but the focus now is on. So these two evolution, homogeneous in time if you want, same group, or time non-homogeneous, generalized one, share the fact of being divisible, and divisible in terms of a CP map. And this is one of the notions that will be used, that we use in order to introduce the notion of memory in quantum mechanics, so in the dynamics of these objects. I now want to provide you an idea of generalizations, so deeper, or at least wider generalization of this Lindblad result. Here I've pointed to the fact that you can allow for time-dependent coefficients, provided they are always positive. And then now I will also try to give some conditions which you might introduce, given a general local in time or memory kernel master equation, in order to guarantee that your time evolution is indeed well defined. In this situation, everything is under control. The theorem is an if and only if. But what about considering other situations, as was asked before, in which we don't have this composition law? Something can be done. Actually, the problem is still open. So let me start. So first question is time local master equations. Yeah, I will be, in a sense, brief. I've given the general idea, and I'll point to conditions which warrant complete positivity. This is a condition which warrant that these phenomenological, possibly phenomenological evolution equations are indeed well suited to describe quantum dynamics. As we learned from the projection operator technique, it is generally the case that you can write down your evolution equation in a form which is local in time. Now, building on the result by Lindblad, its generalization, and on the fact that we have different constraints that we have to keep into account. We have to preserve hermeticity, the operator, trace, and then positivity, and in particular complete positivity. Now, the difficult part is complete positivity, as you might have understood by now, but hermeticity and trace essentially fix the general structure of a time in local equation. And the structure amounts essentially to the Lindblad one, apart from corrections, which means that time in local I will call TCL to remind from the fact that these kind of equations might be obtained exploiting the general techniques of projection operators local in time, as a contribution which is of Hamiltonian form. This will be also there for an isolated system, and another contribution which indeed, if you want, is in Lindblad form, but in order to say Lindblad form, you should say something special about the coefficient. So it's a kind of a generalized Lindblad form in which you allow for time dependence in the operators. You still have the action to the left and of the joint to the right, and the anticommutator term is essentially determined by trace preservation. So hermeticity and trace preservation says that the structure has to be of this form. And that's also the reason why they appear always together. So you take here your k dagger of t, lk of t, anticommutator with rho s. So this is, it can be shown that it's easy to show that actually an equation which preserves hermeticity and trace has to be like this. Now the question is, okay, but if we also want this to be a well-defined dynamics, so in the first instance, this should generate time evolution from time 0 to t, which has to be completely positive trace preserved. Are we able to give conditions in order to obtain this? Otherwise stated, do we have the most general conditions on the time dependence of these objects in order to warrant this property? So the answer is no, there are only partial answers. One has already been written there. It will come clear when I give the conditions for these objects. So in specifying the equation, the operator structure is for sure relevant, is most relevant, but the operator structure, so this L, a joint, and the commutator, is essentially fixed by trace preservation and hermeticity. No, generally not. And now I come to the condition for this coefficient, which should help in clarifying this point. So, given this structure, what about, if you want, I can put it like this. What about P or CP of this collection of maps, which is by definition, a quantum process? Now, one statement is already known. If we say that the coefficients are positive at any time, then we have two things. This collection is CP by construction. Not only, it is also CP divisible, which is something more. So we also have a composition law. This dynamics is well defined and we know the composition law. So CP plus CP divisible. Then another result is known if the sum over k of this gamma k of t times the modulus of un is a possibly a possible complete orthonormal system in the space of the system. So what I'm doing here, I take the Lindblad operator, is matrix elements with respect to an arbitrary orthonormal system in the space of our system, the non-diagonal terms, so I ask n different from m. I take the modulo square of this quantity, sum them with these coefficients, and ask this quantity to be positive. It's maybe the meaning is not necessarily obvious, but this is a condition which actually came about as the result of work done by Kosakowski, actually in the early 70s. At those times, there was the idea to move from the classical to the quantum setting and describe dissipative evolution. So, for example, consider semi-group evolution in analogy with classical semi-group evolution. So coming from classical semigroup evolution, one considered a collection of mappings which should be positive. In the first days, it appeared that positivity was enough. Then it was realized, thanks to Krauss, that actually complete positivity was the key point, but only later. So the first result by Professor Kosakowski were about the characterization of semigroups built up by single maps which were only positive. And he came up with this condition, which is obtained by analogy with condition on classical Markov processes, which is a constraint between the, if you want, can be seen the transition rates and the matrix element of the transition operator, if you think about your interaction as a transition among levels. And this condition is such that the map is positive, so the time evolution is positive, and in particular it is still divisible. Divisible because this came about looking for semigroups, the quantum analog of semigroups in quantum setting, but only asking for positivity. So divisibility amounts to the fact that you compose forward in time. But each piece that you compose is now simply positive. So this is essentially what is known up to now. So, in particular, if these coefficients become negative at a certain point in time, we don't know about complete positivity of the time evolution, apart from special cases. What are the special cases? For example, the one I've considered before, because that was an exact evolution, though one can point to choices of spectral densities leading to coefficients which at certain times do become negative, but such that the overall dynamics is well defined. So in this sense, this apparently simple part of the structure, classical in a sense because the rates, contains in itself information which has still not been completely extracted about the possibility to describe the well-defined dynamics. Now I go for something about well-defined evolution with a memory kernel. So in the time local case, we know that evolution has to look like this, the evolution equation, because of hermeticity and trace preservation. With memory kernel, the subset is more delicate. There we know very little. But there are a few developments which I want to tell you about. Also because they might help the intuition coming back to the classical setting. So the idea is memory kernel master equation. So what we know is that, of course, they should be something like this. If you speak about the memory kernel, the derivative of the statistical operator is equal to the integral over a certain kernel that you might, for simplicity, take to depend on the difference between the time arguments applied to the state at a time tau. So in principle, you are following the state a long time in order to have a solution. It's for sure natural, given this convolution structure, to look at the Laplace transform quantities. This is natural because then this convolution goes over to multiplication. And indeed, it turns out to be a natural strategy. So with this object, it's also natural to keep in mind this one. So this, by the head, I denote the Laplace transform, and I take u as the variable in Laplace quantities. So the derivative amounts to u times the Laplace transform of u. And here, to the right side, we have the Laplace transform of the kernel times the Laplace transform state. So it looks formally simple, and here you can also formally solve for rho s depending on u as a function of the kernel of the initial situation. But it's of course a formal solution. You need to know how does k has to look like in order to provide you a sensible evolution. Now, how to do that? In order to do that, I step back to the classical situation. I have pointed to the Lindblad result, which is something like the derivative of rho as a gain term and the loss term. But as said, this result was essentially obtained starting from studies building on classical analogy. And what is a classical master equation, often called Pauli master equation or rate equation? It's an equation for these are the components of a probability vector. So in the classical setting, instead of a statistical operator, you have a probability vector, so a collection of positive values summing up to 1. And a typical rate equation would look like you have a gain term in which you start from the site j, and you have certain transition rates from site j to site I. This is the gain term, and the loss term would be the situation in which you are in state I, but you go over to a certain state j. Okay, and here I'm summing over j, of course, sorry. Now, this is often called the Pauli equation or similar. And in the essence, if you want the Lindblad result, one way of looking at it is looking at it as a kind of quantum counterpart of this Boltzmann-like or gain-loss-like master equation. The point is that here you are only taking care of populations, so that they would be the diagonal matrix element in a given basis. Here you only have to take into account coherences. This makes all the difference. Now, given this viewpoint, one could ask, do we have some other relevant input in the classical setting for processes which can be considered to be non-Markovian, so to show up a memory effect? Because in the classical setting, in a sense, we have an idea of what Markovian means, at least of the level of classical processes. So the idea is step back also for this situation to a non-Markovian classical situation and try to build on that in order to come to well-defined and, in a sense, physically well-posed or connected to a physical interpretation evolution equation. So what we have here, the idea is that we have certain classical states, 1, 2, 3, 4, and we can jump in between them according to certain rates. Now, one can slightly generalize this situation, introducing information through a stochastic matrix, which gives the probability to jump from one side to the other. So Pij is typically known as stochastic matrix, and gives it the matrix element of this object gives you the probability to jump, say, from 3 to 2, from 2 to 3, and so on. So this gives the probability of jumps. And this is one piece of information, which is already there in this Markovian description. But then there is another piece of information. In principle, tell me when I'm going to jump. And this could be, in the Markovian case, would be described by a simple rate, meaning that in order to know when you're going to jump next, it is not important to know how much time has elapsed since the last jump. This is a way to describe the Markovian situation, and in this sense, the other piece of info that in general you should provide, which is in a sense fixed in a very specific way for the Markovian setting, but in a more general setting has to be provided as, tell me when I'm going to jump. And there might be a situation where the probability to jump at a given time depends on the elapsed time. This is typically so with buses, for example. They are not Poissonian distributed. So one point is the probability of jumps, and the other is the time in between jumps. This quantity is characterized by transition probabilities. This quantity is characterized by a so-called waiting time distribution, which for the Markovian case has to be of the following form, so exponential form. This is the only situation in which the time which has already elapsed does not provide you any information about when the next jump is going to take place. So the idea is, okay, but let us consider other situations different from this one. So we still give a certain set of probability to jump from here to there. So once I am in 3, I have a certain probability to jump to 4, to 1, or whatever. But I also need to provide information when is the next jump going to occur. So I replace this object with a general setting. And these objects always come together with this companion, which is the so-called survival probability. Which is the probability not to have jumped up to time t. So 1 minus the integral of the waiting time distribution. Survival in the sense, this is the probability not to have jumped up to time t. So it is 1, time t equals 0, because you start from there, and then it basically goes slowly to 0. So these two objects, in a sense, come together. And indeed, the idea is that we can exploit these objects together with this stochastic matrix in order to obtain a class of classical evolution equation which feature memory, in the sense of they give rise to a process which in the classical setting is non-Markovian. Then from there, we will move to the quantum setting. In order to move there, we will replace functions by operators. And when we replace function by operators, there is something special which happens. Operators generally do not commute. So if you have a function which is a product of different functions, and each of them is replaced by an operator, you have to pay attention which ordering you are going to take. And what we will see is that depending on the ordering, you end up with different time evolution equations. So there's kind of wider freedom in the quantum setting with respect to the classical one. So let me close coming to the classical evolution equation, which is the, say, non-Markovian counterpart of this equation, and then tomorrow I will go on to the quantum setting. So just to complete, the evolution equation I've written there is now generalized to the following one. Besides the sum, I introduce an integral over time, because these rates will generally be time dependent. So I will have a sum over j, an integral between 0 and t in tau. My transition rates now are generally time dependent. So instead of wij, I will write wij depending on t minus tau times j times tau minus, this is the gain part if you want, the loss part will be the reverse part. Wji t minus tau pi of tau. Now, the crucial fact is that there is some information in the classical setting how these objects do look like. And these objects can be, in a sense, easily understood if you re-express them in terms of this pi, this f, and this g. So that is the. And then this will be moved on to the. Okay, now, since I have only 1 minute, even if I would need a lot of time, it's better to waste these seconds rather than start a new topic. So thank you for your attention. Sorry? The reference given here covers today, and the end of today and beginning of tomorrow will need other references, and these I will provide.